Okay, so today we're going to talk about stars. This is to be quite there's quite a lot of information here, quite a lot of new information, and really this will probably be broken up into two classes today and tomorrow, at least part of it. All right, you do have access to this PowerPoint, by the way, which is pretty useful for us. So what we're going to talk about is obviously stars. A lot of this presentation will focus around this specific constellation. Anybody know what constellation this is? I know it's a little hard to see maybe, but if you have it pulled up on your screen. And particularly notice these three stars here, which make up probably the most recognizable feature. Nobody? It's Orion. This is Orion's belt here. Beetlejuice is sort of his shoulder, and Rigel is down here. So you can see here, he's got a bow, an arrow. He's got a bow here. He's got his hand back, ready to get an arrow. And this is supposed to be like his sort of torso, and his legs down here. They had good imaginations, you know. They saw this stuff every day, so they had to come up with something for it. Anyways, this is Orion the Hunter. So let's talk about the very basics. What's a star, right? So I think if I asked most people what's a star, they would say it's like a ball of burning gas or something like that. And that's not right. It's not a gas. We talk about the states of matter. The sun is too hot to be a gas. So the sun is actually made of what we call plasma. So a star is a ball of plasma. It's predominantly made of hydrogen and helium. Again, if you look at the composition of a star, it very closely mirrors the composition of the universe, right? So it's going to be 98% of it is hydrogen and helium. Actually, it's probably even higher than 98%. It's probably almost 100%. Because those heavier elements, there may be some present, but a lot of those heavier elements go around a star to form the planets that surround it. The stars, all stars go kind of in order from the surface temperature is the coolest to the inside, what we call the core, is the hottest and most dense. In fact, because it's so hot and so dense, a process called nuclear fusion can occur in the core of the star. And this is important because that's where all of the energy for the star comes from. Obviously, stars emit huge amounts of energy. All life on Earth, right, is sustained from the energy emitted by a star that's like 96 million miles away. You know, you think about trying to like heat up a room, you got to get pretty close to the heating coil to stay warm. If you've ever seen sort of those radiators, they do an okay job of heating up the room, but obviously, you know, once you get further away, they don't work so well. Well, the sun, again, is 96 million miles away, so we receive some incredibly small percentage of the energy that our sun puts out, and it's enough energy to sustain all of life on Earth. Like all energy on Earth, with very few exceptions, right? We're talking about like geothermal exceptions, but everything else, all energy can ultimately be traced back to the sun. This process of fusion is important because it converts light elements into heavier ones. And again, we talked about Big Bang Theory predicts how the first elements are made, basically hydrogen and helium. Everything else is produced through this process. So again, our bodies are made out of a lot of carbon, a lot of oxygen. All of those carbon atoms, all of those oxygen atoms come from the core of a star at some point, is where they're made. Okay, we discussed this previously, but stars obviously in the night sky are different. And two of the biggest differences have to do with luminosity. Luminosity is how bright a star is. Clearly, Beetlejuice and Rigel are much brighter than, you know, these stars in the background is certainly, you know, they're brighter than a lot of these areas. But they're also different because they have different colors. Beetlejuice, you can see, is clearly a red star. Rigel looks like a bluish white star. That color tells us a difference of temperature because, as we discussed previously and as we're going to discuss in a moment, the color or light that's emitted by a star tells us, you know, its temperature. It's radiating, how much energy it has that it's radiating away. Okay, so luminosity is measured in something called watts. This is also, you'll may remember, the unit of power, right? Energy or power is in watts, and power is really just energy per second. So a watt is a joule per second. So a light bulb, typically 10 to 20 watts. The sun's luminosity is much bigger. So again, it's because it's so much bigger, this is how we get our energy here. So again, that's how many joules of energy is released by the sun every second. And the truly astonishing thing is that the sun's been doing this. It's been, we believe our sun to be about 4.6 billion years old, and it'll still do this for another 4 billion years. It's actually, it's just amazing how much energy they put out. So we can measure the luminosity of other stars as compared to our sun. And as we'll discuss in a minute, our sun is pretty average in a lot of ways. All right. I think we already know about Kelvin. If not, very basic. Kelvin is a scale of temperature. And to get a Kelvin, you take the temperature in Celsius and add 273. Kelvin is what we call an absolute scale because it has what we call absolute zero. So 0 Kelvin is a temperature where it's so cold that there is no energy, there is no molecular movement remaining. Okay, so the color of a star is going to indicate its temperature, and it follows the spectrum as we previously discussed. So red stars are the lowest temperature, and again, when we say red stars are cold, obviously they're stars. You would instantly be incinerated if you got within 1 million miles of them. But we're saying relative to other stars, the red stars are colder and the blue stars are hotter. So the sun, we're going to calculate its temperature in a minute, but you see it's about 5,800 Kelvin. Beetlejuice is about 3,000 Kelvin. And again, I want to emphasize these are surface temperatures, right? So the color only tells us about the surface temperature. The cores get much, 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 much hotter. Rigel's surface temperature indicates it's about 12,000 Kelvin. So again, a huge difference between these two stars. Okay, so this is how we can calculate the luminosity of a star. Specifically, this has to do with what we call a black body. So again, we assume this is an object which we assume perfectly receives energy and perfectly radiates energy away. And you have some interesting features here. Okay, so the luminosity is going to be equal to, this is a constant. Again, you don't have to worry about this. It's just a number. So we will do some calculations with this. You'll notice here the sigma is what this is, the letter sigma. Is 5.67 times 10 to the negative 8. That's just a constant. These are just units back here. So you don't do anything with the units. It's just like the name of the constant, right? So this is the important part of the constant. So there's some constant, and then you're going to multiply by the surface area. So again, if an object has more surface area, it will have a greater luminosity. And finally, you see temperature to the 4th power. That's a huge factor. I mean, raising something to the 4th power makes it pretty, even one of the smallest numbers, 2, right? 2 to the 4th power would be 4, 8, 16, right? 2 to the 4th would be 16. So, and that's the smallest one. I probably couldn't even calculate 3 to the 4th power without the use of a calculator. It's just so, to the 4th power is a big deal. So whenever you look at this and we say, okay, what term, right? There are 3 terms here. Which of these 3 terms is going to really dominate this equation? It's going to be this one right here. If you have more temperature, you will have more luminosity. Now you can calculate your luminosity, right? You can calculate your luminosity doing this, right? You get some approximation of surface area, right? You have to have that. You multiply by this, and you multiply by your temperature to the 4th power, and you see your luminosity. Okay, so as I just previously said, black body is something which absorbs all wavelengths and emits all wavelengths. Stars are pretty good approximations, so when we look at the temperature of a star, we can be pretty confident because they are good black bodies. So when we're going to use Wien's law in just a second, the intensity of each wavelength so is going to depend on its temperature. So the temperature is going to relate to the wavelength as we previously discussed. And so it might surprise you, right? And we're going to do this calculation in just a minute, but when we look at and say, okay, the sun has a temperature of 5,800 Kelvin, right? I mean, we've never been to the sun. It's not possible. You can't. We can't. We can't send like a probe to the sun and measure that. It would melt. I mean, it would just melt way before it ever got there. We can't do that. So how do we know the temperature? Well, we use these equations to do that. Okay, these are our blackbody curves. We looked at a few before, just another example here. So when an object has a temperature, it is emitting energy at different frequency or wavelengths. So you see down here, this is called a brown dwarf. It's the coolest type of star. Brown dwarfs are emitting energy. The peak wavelength is in the infrared portion of the spectrum. Now, brown dwarfs are hot enough that they probably are emitting some visible light, so they would probably look like, again, almost like a toaster oven. If you look inside a toaster oven or you look at the eye of a stove after you turn it on, they emit some light there. And so they would probably, you would probably see it, but it wouldn't glow that brightly. Obviously, a sun is a different story. It's very, very bright. And you notice that the visible wavelength, right, the peak is right in the visible light. It's right near the yellow, which again is why we perceive the sun to be yellow, because that's most of the light that comes to it. But our sun is emitting all kinds of light. This is how rainbows can form in the first place, because our sun emits lots of light, and so you pass that light through a prism or a raindrop, you can get this spectrum back out. You can see all the light. And again, there's even more parts of it that we just can't see. We can't see infrared, or we'd see more stuff over here. We can't see UV, or we'd see more stuff over here. But obviously there is UV, and that's how you get sunburns. And one more time to emphasize, you'll notice this peak is right in the middle of what we can see. That's not a coincidence, right? Our eyes evolved to see what most light is, and most light from the sun is in that section. Therefore, our eyes have evolved to see all of these colors in particular. This is called a gamma ray burst. I have previously mentioned it briefly, but gamma ray bursts are there are huge amounts of energy output by a dying star. We'll talk more about them later, but they're very, very narrow, but they're incredibly dangerous. I mean, again, this is our sun here. This thing is just completely dwarfing our sun. And as you go up here, you may not notice that this on the x-axis, this is logarithmic, right? So the difference from here to here isn't like okay, 1, 2, 3. It's like 10, 100, 1,000, 10,000, 100,000. I mean, so anyways, this peak, right, is so much higher that it's incredibly dangerous. In fact, it would almost certainly, if a gamma ray burst were to come and hit us directly, would almost certainly knock out all life on Earth. Okay, so let's see if we can figure out how hot the sun is. Okay, so this is, you can use a special machine. Specifically, this is a spectroscope. A spectroscope can look at and see what kinds of wavelengths are coming into to us from the sun. And we find out that its peak wavelength is about 0.5. This symbol right here, by the way, is the Greek letter mu, which gets used for micro. So about 0.5 micrometers. So it'd be micrometer is a millionth of a meter. We can calculate the temperature of the sun using something called Wien's law. Quite simple, but there's the equation. So the temperature of an object is going to be equal to this is just some constant, the constant for Wien's law, divided by the peak wavelength. And we want the peak wavelength in meters. So based on what we see, let's see if we can calculate this temperature of the sun. Okay. All right, so I'll get a larger pen size here. I'm gonna write down the information. I'll bring it back over here. All right, so temperature is gonna be equal to B divided by peak wavelength. B is equal to, again, it's just a constant. You don't have to memorize these. You'll have them, obviously. 2.898 times 10 to the negative third. And then we saw that the peak wavelength for our sun, for our star here, is 0.5 micrometers. Okay, so let's see if we can calculate this. Again, even though the numbers might be kind of strange, the application of them is pretty straightforward, actually. First thing I'm going to do is I'm going to put this into just regular meters because I didn't put the units on here, but this has units of meters, this constant, so I have to have this in terms of meters. So that would be 0.5 micrometers. Micrometers to meters. I know that there are 1 million micrometers in 1 meter. So I got 0.5, these cancel. So I just have meters, which is what I wanted. 0.5 times 10 to the negative 6th meters. Okay, so back over here, the temperature is going to be, B is 2.898 times 10 to negative third divided by 0.5 times 10 to the negative 6th. And this should give me my temperature in Kelvin. So I'm putting that in my calculator on top. 2.898 times 10 to the negative third divided by, on the bottom, 0.5 times 10 to the negative 6. All right, and even though it looks kind of ugly, the number I get at the end isn't that strange. 5,796 Kelvin. So there we go. We were able to measure the temperature of the sun simply by looking at its peak wavelength. What was its peak wavelength? And we know that that peak wavelength corresponds to a temperature using Wien's law. So we didn't have to leave. We didn't have to go anywhere. We looked at the light that came to us, and we could tell the temperature of that star. This works with any kind of star, right? We can do this for any star that we like, as long as we can measure its light. You'll see that worked out there, but again, exact same thing we just did. So that's, and again, I want to emphasize, that's the surface temperature. If a star was that temperature all the way through, nuclear fusion would not be possible. It's much, much, much hotter in the core of it. Okay, so let's start looking at how we can categorize lots of stars. Now that we know how to calculate their temperature, we obviously can measure the luminosity. How can we categorize these stars? So what we're going to make is what's called the HR diagram, Hertzsprung-Russell diagram. So you have two axes here, okay? Let's look at these axes. The one on the y-axis here is luminosity. Its unit is relative to the sun. So a star which has the same this exact same luminosity or brightness as our sun would be a 1. Again, this is a logarithmic scale, so you'll notice it's not like this goes up by 1, 2. It doesn't go up by the same amount every time. It's a factor, so it's because it's 100 times. So this right here is 10,000. That's 100 times bigger than that. And this 100 times smaller and 10,000 times smaller. On the x-axis, you have the same thing. The only thing that's kind of weird is you would naturally think that 0 Kelvin would be on this part right here, the origin, but it's actually reversed. So this side is the hottest, and this side is the coolest. So 0 Kelvin would be all the way out here somewhere. And this side is actually the hottest. Okay, so let's start with the most basic question. Where would our sun be? Well, how bright, relative to our sun, how bright is our sun? So relative to our sun, right? This is how bright compared to our sun. So how bright is our sun compared to our sun? Is it 100 times brighter than our sun? Is it 1/10 as bright as our sun? So our sun, relative to our sun, would be a 1. So clearly it's going to be a 1 here. Okay, we just calculated the temperature of our sun, right? We got like 5,900 and something. We'll call it 5,000. It's a little bit to the left of 5,000 here. So if I put that there, it should be somewhere in this area. And that's where we see our sun. Okay, it's a little bit off on that side. Okay, simple enough. Now we just do this for other stars. Okay, Vega and Sirius are 2 stars that are brighter than the sun and also hotter. Okay, so we're starting here at our sun. Let's do luminosity first. It's brighter, so do I go up or down? Yep. Again, these are bigger numbers up here than these, so you go up. If it's hotter than our sun, do I go left or right? Yep. So it should be over here. Some stars are much cooler and less luminous. So the one nearest to the sun is called Proxima Centauri. Okay, so this is called a red dwarf. Okay, it's cooler and not as bright. It's dimmer and cooler. So if it's dimmer, do I go up or down? Down. And if it's cooler, do I go left or right? Should go right. So what you can do is you can do this for every single star. Again, we're not doing like specific numbers, but you could take the specific temperature, the specific luminosity, and you could create a graph of these stars. And what you find is that 90% of these stars that we can see fall right into this into this area, and it makes this kind of curve, what we call the main sequence. So our sun is a main sequence star. All of these you see, main sequence stars. And it makes sense, right? Because remember how important temperature was. If something has a high temperature, it probably has a high luminosity. Likewise, if something is pretty cool, it probably doesn't have a big luminosity. So again, this makes sense with what we'd expect. Bright stars are really hot. Dim stars are not so much. Okay? But not every star is there. Okay? 2 stars, the Arcturus and Aldebaran, they're brighter than the sun, but cooler. So if they're brighter, so from the sun, if they're brighter, do I go up or down? Up. And if they're cooler, I go to the left. To the right. So they'll actually be in this area over here. They're called red giants. So there's something different about these stars, right? Because they're not in this main sequence that makes them different. Next, we have Beetlejuice. If you remember, Beetlejuice was the sort of shoulder of Orion at the very beginning. So Beetlejuice is even brighter than Aldebaran, but it's also cooler. So again, we follow the same pattern. Even brighter, but also cooler. It's going to be over here. This would be called a red supergiant. Okay, stars like even brighter than Beetlejuice. So wow, we're still going up even more. Deneb and Rigel, they're much hotter, so they would be to the left side. They're actually blue, and then so they're called blue giants. Okay, those are actually, if we have found some stars like Sirius B, which are some of the hottest stars we've ever found, but they're much fainter than the sun. And they would be in this area over here. So very hot, very faint would be in this area. These are called white dwarfs. So what we're actually seeing here are stars at different points in their life, right? Stars have a finite lifespan, right? They're going to start in one place, they're going to move around, but they eventually are going to die. So these stars down here, these are kind of like dead stars. They're the leftover parts of stars. These are stars that live most of their life, and these are stars that are almost dead. They're about to die. So as a star like our sun is going to move around, it's going to move around the HR diagram throughout its lifetime. So our sun has been in the main sequence for about 4 billion years already. We expect it to stay there for 4 billion more. But eventually what will happen is it will start to swell. We'll go into more details later, but the sun will get bigger. As it gets bigger, it becomes brighter but cooler. So again, if it's getting brighter, it's going to move up this way. If it's getting cooler, it's going to move this way. So it's going to move out into this area. And as you can probably guess, it's going to become a red giant. Then right before it dies, it's going to get incredibly hot and move over here and be called a blue giant for a moment. It's going to shed those outer, it's going to shed these outer layers and eventually end up over here as a white dwarf star, where it'll just be leftover core of a star. Okay, let's talk about nuclear fusion here. All right, so the luminosity of a star is powered by nuclear fusion, and this takes place in the center of the star. The most basic form of nuclear fusion is where we take hydrogen and fuse it into helium. Okay, if you remember from a periodic table, the very most basic element is hydrogen. Notice that there are no electrons involved here because you'll remember the sun is a plasma. In a plasma, the electrons are moving around. They're away. They're gone. So these hydrogen atoms are really just protons, really. So these two protons are going to come together. They're going to, one of these protons, so the process is one of these protons releases something called a positron and a neutrino and becomes a neutron. Then it collides with another hydrogen or another proton, and that creates this helium atom. This thing right here is supposed to be a photon, and it's energy being released. Okay, so again, you see the process here. I'm not going to ask you about the very specific details. The general thing I want you to know is that hydrogen forms into helium. And the important thing is, you'll see in just a minute, is that there's a little bit of mass that's lost in this process. So when you see these little things right here, like this neutrino, that's some energy sort of being released, this particle being released. These are actually predicted long before they were found. But our sun emits them all the time. But this right here, this is a gamma ray photon. That's energy being released. And so the reason why that energy is being released is because if you add up all the components here, they have slightly less mass than all the components here. According to the conservation of mass energy, if we have a slight change in mass, that it can't just disappear. It gets turned into energy. Okay, so once again, the whole process is hydrogens are coming together, and then they are eventually, at the end, you have a helium. It's got cut off there, but this is He because it's got two protons. So there are two forces at work in a star. Okay, this nuclear fusion produces, it's basically like an explosion, right? When we talk about a nuclear bomb or like an atomic bomb, that's what's going on. You have a nuclear fusion process, and it's uncontrolled, so it's basically an explosion. So you have explosions pushing out, and you have the force of gravity pushing in. And so for a star like our sun, it is balanced, right? The nuclear pressure pushing out is exactly equal to the gravitational pressure pulling in. And so our sun is not changing, really. It's like it said, it's been the same for so long, and will continue to be the same for so long because it's not really changing. But that will change at some point, right? So our sun has been using up its hydrogen. So as it's been using up hydrogen, again, it still has plenty to go on for a long time, but eventually the amount of hydrogen it is fizzling out as the amount of helium has increased. So at some point the hydrogen runs out, and that outward force is reduced, right? You don't have as much pushing out. And so then you have an unbalanced force, right? Because they were balanced, but if I reduce this force, then this outward gravitational force is going to win. It's going to push in. So the star starts to collapse, or at least the core of the star starts to collapse. If the star has enough mass, then you get a new type of fusion, right? Because as it collapses, the temperature goes up way, 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 way up as it starts to collapse. You can have a hot enough core that you start to do a different type of fusion. and you get helium fusion, right? And notice the temperature here. When the temperature is greater than 100 million Kelvin, okay, so it's insanely high temperatures. But if it's hot enough, what you can do is you can start to take helium and fuse it into carbon. Well, hey, that's good for us because we're made out of carbon. So good thing that happens. These helium come together. Again, energy is produced. You get beryllium, another one, and you get carbon. So the sun just starts to fuse carbon at this point. Okay, so the carbon nucleus can then fuse another helium nucleus to make oxygen. Hey, good thing that's made because we're made out of a lot of oxygen. So again, this is where it's not a coincidence that, you know, if you look at the most abundant elements, we happen to be made out of 2 of the most abundant 5. Okay, eventually this stuff starts to run out though. So you get these different shells in a star. And it's all dependent on the mass of the star. If the star has enough mass, it'll continue to crunch down, it'll continue to collapse and then generate more heat. And then if it has enough temperature, has a high enough temperature, it'll keep fusing heavier and heavier elements. Okay, so the total you can see here, it can fuse up to neon, magnesium, silicon, and iron is the kind of the stopping point here. Once it starts to fuse iron, and only the heaviest stars will fuse that. The sun will never fuse iron. Our sun will fuse probably some oxygen, and that'll be it for our sun. But the really massive stars can fuse all the way up to iron. The problem with fusing iron is that it takes as much energy to fuse as you get back out. So up until this point, right, you could get more energy out than you put in. So here for the most massive star, this is what you would see. You would see all these shells here. So you'd have hydrogen on the outside, helium, you'd have a ring of helium, carbon, neon, oxygen, silicon, and then finally the very center would be iron. Let's look at a little bit of the specifics of how this produces energy, right? So here you see the hydrogen fusion process. Again, you end up at first you have 6 hydrogens, and at the end you have a helium, 2 hydrogens, and 2. This is called a positron. It's the opposite of an electron, basically. Okay, so what happens is that the mass of the products, so this is the products, are less than the initial mass on this side in both cases. So in every one of these reactions, mass is being lost. This is not something I want you all to be able to do, but it's just something we want to look at real fast. So if we look at this process, right, 6 hydrogen, this is the atomic mass of hydrogen. Atomic mass, anyways, these are masses. So we add all the masses up. Again, there's a difference here. This is slightly heavier than it was before. And so the difference lost here is this, which is an incredibly small amount, right? 10 to the negative 29 kilograms. That's pretty small. But, right, E equals mc squared. This little tiny bit of mass is going to be turned into energy by multiplying it by the speed of light squared. So here's the speed of light squared. Multiply it together, and that little tiny bit of mass ends up being, again, still a pretty small amount of energy, but relative to the amount of mass, it's a lot bigger, 10 to the negative 29 to 10 to the negative 12. So this is how much energy is produced in that reaction. And of course, once you do this billions and billions and billions of times, then this number starts to become quite significant. We're going to skip this one, but it's the same thing. Now, I will point out this one is less, okay? You get less energy back out every time you go up and fuse a heavier element. Okay. We're going to stop there for today. There was one more point I wanted to make here. Let me see if I can find this real fast. I thought it was in there, but I guess it's not. But this is what I'm looking for anyways, I think. Let me just look up the... Okay. Okay, so this is what you get when this is called the binding energy per nucleon. Basically, this is how much fusion produces, right? So fusion produces energy up into this point right here. So you can think of it as the difference between here and your product is how much energy you make, right? So look at the gap between this is hydrogen and the helium that you produce. This is a huge gap here. In other words, it's a lot of energy that you get out. Okay, then for the second one, right, if you remember we take helium and fuse into carbon, not as big. Fuse into oxygen, not as big, right, but it still gives you a little bit. Oxygen to neon, neon to magnesium, anyways, you get up to iron. Well, what do you notice here at iron? It's flat. At this point, you don't get any energy out when you try to fuse iron. And that's why when a star tries to fuse iron, that's when it's gonna die, because there's no matter how big the star is, no matter how hot it gets, it's not going to produce any more pressure back out. It's not going to produce any more nuclear pressure back out. Therefore, gravity is going to make it collapse. And we're going to go into more details about that later. Though here's the way I like to think about it. Imagine that I said tomorrow, for every, if you bring me $1, right, for every $1 you bring in tomorrow, I'll give you $20. I'll give you a $20 bill for every $1 bill you bring. Of course, you'd spend the rest of your day finding $1 bills, because that's insane. You get all kinds of money back. Okay, obviously money in this case is energy. That's a good deal. You take that all day, $1 for a $20 bill, that's amazing. Okay, now we're going to fuse helium. Okay, the equivalent of that would be, okay, for every $10 bill you bring in, I'm going to give you a $20 bill. Well, you'd still go crazy and get as much as you can. Of course that works well. Then we start fusing heavier elements. Maybe we're starting to fuse up to carbon or up to oxygen. And I say, okay, well, if you can bring me a $10 and a $5 bill, I'll give you a $20 bill. Again, obviously a good deal. Keep going. Finally, you get to iron. And I say, okay, if you bring me $20, I'll give you $20. I mean, what's the point? You don't get anything back out. That's exactly what's happening in the fusion of iron. As iron gets fused together, no energy is released in that process. And so if there's no energy released, then there's nothing to sustain the star, and the star will just collapse on itself. You'll notice here on this end, this is the energy produced by fusion. The gap on the other side is the energy produced by fission. That's where you break apart a molecule. And that's actually what gets used in nuclear weapons, is nuclear fission. And again, you see that there's quite a big dip down here. One of the most common products is uranium for creating a nuclear fission, which you probably heard of before.